Okay guys, welcome back to another video. Today we are going to use the extended principle of mathematical induction to prove the following example. Okay, here and here. So take a look at this example. We want to show that 3 raised to the n greater than n to the power of 3 is true for every positive integer n such that n is greater than or equal to 4. So go back to take a look at the extended principle of mathematical induction. To prove, to use this principle, we have to show that P of A is true, which is base step. And then we have to show that for any integer k such that k greater than or equal to a, if P of k is true, then pk plus 1 is also true. If you can prove these steps, base step and inductive step, this is inductive step, we can show that Pn is true for every integer n such that n greater than or equal to a. Now let's prove this. We want to prove that n 3 to the n greater than n cubed is true such that n greater than or equal to 4. So let's prove this. You might try to plug in n equal to 3. Right? When n is 3, you're gonna have 3 cubed and 3 cubed. Okay, when n is 2, you're gonna have 3 square greater than 2 raised to the 3, which is false. No, sorry, which is 9 greater than 8. Okay. That's interesting. When n is 1, what happened? When n is 1, we're going to have 3 to the 1 greater than 1 cube. I just try to plug into you. Alright, so now let's prove it. So we let P of n be this inequality 3 to the n greater than n to the 3. Okay, and then we will show that Pn is true for any positive integer n such that n greater than or equal to 4. So we start with the base step, and we will use the extended principle of mathematical induction. The base step is try to plug in n equal to 4. So we're gonna have 3 to the 4, which is 81, which is greater than 64, which is what value? 4 to the 3. Okay, good. So this means that P of 4 is true. Okay. This means that P of 4 is true, so we already proved the base step. Now, what about the inductive step? To deal with this, we have to show this. Okay, so we have to assume that for any integer k, okay, such that k greater than or equal to 4, okay, and P of k, I gotta write just P of k is true, okay? Is true. And we're going to show that P of k plus 1 is true. So what do we have right here? When pk is true, we're going to have 3 to the k greater than k to the 3. And then we have to try to show that P of k plus 1 is true. That's what we have to show. So now what can we do? We want to start from 3 to the k plus 1. Now, what is 3 to the k plus 1? 3 to the k plus 1 is 3 times 3 to the k. Okay? And then, what can we do? Okay? What can we do next? Then, it turns out to be, so we have 3 times 3 to the k. This means that we have 3 terms of k, right? Okay? 3 terms of 3 to the k. Okay? So you might just use this one, right? So, since we have this one right here, 3 to the k greater than k cubed, we gotta have k cubed plus k cubed plus k cubed. Then, what next? Then, here's what we have. It's going to be greater than k cubed plus 3 times k squared plus 3 times k squared. Alright? Okay? That's what we have. Why? Because k, so k cubed is going to be greater than 3k squared. Okay? And k cubed is greater than 3k squared. Because k is greater than 4, this means that just k greater than 3. Okay? So k cubed, we know that is k times k squared. But we know that k is greater than 3, so we gotta have greater than 3 times k squared. Okay? So, we have this one because k is greater than 3. Now, what next? Okay? Do the same thing with this k squared again. So it's greater than, okay, we have k cubed plus 3 to the k. Now, what about just k squared? What is k squared? K squared is k times k. And k is greater than 3, right? So it's going to be greater than 3k. Okay? It turns out to be 3 times. We know that k squared is 3 times k. Alright? And then we try to calculate. Then it turns out to be k cubed plus 3k squared plus 9k. Okay? And we partition 9k. Then it turns out to be k cubed plus 3k squared plus 3k plus 6k. Okay? And we know that k is greater than or equal to 4. Then we gotta have greater than or equal to k cubed plus 3k squared plus 3k. because k is greater than or equal to 4, we're gonna have 6. This term 6k is going to be greater than or equal to 6 times 4, because k is greater than or equal to 4. That's the reason. So we gotta have 6 times 4. Okay, then it turns out to be right here, it's going to be k cubed plus 3k squared plus 3k. 6 times 4 is 24. I gotta partition 24 into 1 and 23. Okay, 1 and 23 like this. And then this first 4 term right here, we know that it is k plus 1 cubed plus 23. And this one right here is going to be greater than k plus 1 cubed. Okay, so right now I have inductive step already. From what we have right here, 3 to the k greater than k cubed, we have 3 to the k plus 1 greater than k plus 1 cubed. Okay, so we're gonna have, hence, right now we have 3 to the k plus 1 greater than k plus 1 cubed. Okay, for any integer k such that k greater than or equal to 4. So we have proved the inductive step already. Therefore, we've shown that 3 to the n greater than n cubed. Okay, for any, so this inequality is true for any positive, for any integer k. Okay, such that n greater than or equal to 4. And this is how to use the extended principle of mathematical induction. So in the next video, I'm going to show this equation, n factorial equal to this one, right? And we're going to prove that n factorial greater than 2 raised to the power of n for every positive integer greater than or equal to 4. That's it for today, and see you in the next video.